or what are the inputs or weights where we can apply this quantization. Okay. First, you can see this the top part it is showing this mentioning about weights, and this lower part it is mentioning about the outcome of the activations. Okay. Now, I want to ask you one thing. You know about different activation functions, right? So, can you tell me for one activation function, if you control properly, that may always give you integer output. Okay, first tell me what type of activation functions you know. Anyone?
Ma'am, Signum will always give integer values, right? Signum or
Sigmoid.
no, not Signum.
Signum. Okay. 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 Fine. Okay. Okay. Fine. We will see some more. Let's start with this. So first one is the weights, and the next one it is about this part we are discussing about the outcome of the some activation function. So when we are talking about weights, this as we mentioned, this purpose all are these are quantized data. Now when we are quantizing, we have, let's say, a floating point represented weights like some 5.324 or something. So we are chopping them or we are clustering them together, very close values. We are clustering them, we are sharing them, we are bringing them into one group. Okay. With that, we are maybe this 5.324, 4.897, all these values we are clustering together, and maybe we are mapping them to some integer values, some integer values. Maybe that is 5. Okay. So that is where one way of how we are clustering weights, and the values we are quantizing. That is one quantization technique, simple quantization technique. Next one is the post-train quantization. Post-train quantization means we all know that we have two steps. So in the first training step, whatever processing we are doing, there we are considering all weights are floating point weights. But once the training is done, we have done all sort of back propagation steps. We have updated our weight parameters. Those steps are done. When we got the final weight, after that we are applying some amount of quantization with this type of, let's consider this type of truncation, and then we are taking the integer value. That is called post-train quantization. Next one is the quantization over training. Okay, that means not only in test step but also in training step, we are considering, okay, some weights or some input values we can chop, we can quantize, we can bring within a particular range, and maybe we can deal with integer values, and that way we are quantizing our training data. Maybe it may be training input, it may be training weights. Okay, so this is quantize about training. Okay, in these steps we can see two terms. Okay, one is non-saturated activation. Okay, before that, when we have done this weight, we have considered this clustering of weights, it may happen, or in general, the activation functions we are using, that is giving you some floating point output. Let's consider the sigmoid. Okay, this type of this sigmoid function. In this sigmoid activation, of course, you know there is a range. Within that range, whenever the outcome you are getting, that is a floating point. Similarly, in case of post-train quantization, that means when you are considering the considering quantization only maybe on the test weight values that you are considering in the test phase. There you are applying the quantization, but the activation outcome, that is you are handling with some floating point values. Modification came after that when we considered non-saturated and saturated activation functions in a different way, and then we have applied some calibration, and there we got this type, this the outcomes we got, that is also integer. Those that we got some quantized values of this activation function, outcomes of the activation function. We will see this part in detail, how, what we mean by non-saturated, saturated, and how we can what is their difference. We will come later in. So in this diagram, what we discussed, basically only weights are quantized initially, then quantization of weights along with clustering, sharing, quantizing, and initially that showed huge reduction in network structure. Then came the post-training quantization that involves taking a trained model, quantizing the weights, and then re-optimizing the model to generate a quantized model with some scales. Okay. Next, as we talked about all this, we are applying this quantization also in the training phase. Now comes this saturated quantization. Okay. Now, to understand that, first understand the different types of activation function. Now, this is I have written as your assignment because you will I will just here give you the idea of what we mean by saturated and non-saturated with two examples. One is sigmoid and one is ReLU. Okay, and then it will be your task to go through all other types of activation functions that maybe we have not discussed in detail in the class. Like TANH, maybe TANH we have mentioned. We have some more ReLU, VeLU, leaky ReLU, PReLU. So you will do one exhaustive search in this. What type of activation functions we may need when we are dealing with the CNN, DNN type of things. And then there's architectures, and then you will classify them as with which one is saturated and which one is non-saturated and why. The main thing is the which one is saturated and which one is non-saturated. That is written here, doesn't matter. So you will just identify based on one input what will be the output shape, and based on that you will comment why you are classifying them as saturated and non-saturated. Here some mention there, we have mentioned some activation functions, but you have to search some more. Okay. So when we are talking about saturated means it is within a range. Okay. Why I have taken this sigmoid? See, when we are taking the outcome of the sigmoid activation function, it always remains within a range 0 to 1. Among them, these values will land. On top of that, whatever value you choose, whatever outcome value you may have, you may get, that is either close to some maximum limit or some minimum limit. Okay. So that way, that's why we term it as saturated. It cannot go beyond these boundaries. It is bounded. And that way we term it as saturated. Well, if you check for TANH also, there we will see this boundary will change. Here we are mentioning 0 to 1. In case of TANH, you will find that the shape will be quite similar. This shape, H shape, but this boundary will change. Okay, it will -1 to +1. So that way, this these type of the sigmoid, TANH, these type of for this type of activation functions, whenever you are taking any outcome, that is mostly close to either the max level or the min level. Okay. Whereas if we take the another type of activation function, that is ReLU. What we do in ReLU is this type of, it gives this type of output. Okay. Max of 0 and Z. Z may be your input. Okay. You are computing the max. So in this case, you are basically taking one max value. Okay. But that is based on your input, you are defining your max value. But that is not it is not like it is related to any range or it is bounded by any range. and that way it is non-saturated. Okay. We will see some more advantages of ReLU while we are talking about quantization, etc. Okay. So that way, now you understand the meaning of this word. The saturated quantization can be used to generate feature scales using a calibration algorithm with a calibration set. That means if you now see the saturation type of activation function when you are using, you are basically adding some calibration, and that way you are quantizing, and that then you are taking that according to your calibration, you are considering one integer value. Okay, this is one form of quantization. We term it as, in this diagram also, this calibrated saturation. Okay, so from non, that's why you can see these blocks. Now I think the color of these blocks are again clear. So these are blue, and the all when we are talking about non-saturated or calibrated saturated, these blocks are also purple. That means they are also quantized. In non-saturated also, whatever max value you are getting, that is you may avoid, in case of non-saturated value, you may avoid to consider any floating point. You can directly consider that max value as some integer value. Okay, that way it is also some integer block. And in calibrated saturation, of course, direct saturated outputs may not be there in having integer values, but when you are applying some calibration on top of that, and you are taking some integer value according to your calibration set, that way you are getting these activations also, activation outputs, this calibrated saturation activated activation outputs also as integer values. Okay. So is this part clear? So what your job will be to study, to do an exhaustive search of other as activation functions, and to check the shape of those activation functions. So when you will make a report, you will include the shape of those activation functions, and then you will justify why you are terming them as non-saturated or saturated. Okay. This part we will come later. Now, we have talked about multiple terms, this quantization, activation, sparsity. Okay. We will see that now one thing you can understand, right? If you applying this type of calibration, okay, with this proper calibration and choice of proper calibration set, you can actually map some near to zero weight values to zero weight values. And whenever we are doing that, with that calibration, you are mapping some near to zero values, close to zero values, to some actual zero values. That means when you are computing, remember our previous day discussion, when you are getting that way zero weight values, basically you are skipping any computation related to that. Because as we discussed, weight into some value, always zero, so no point computing on that. Whenever we are checking that, okay, my weight value is zero, let's keep that huge multiplication. So you are saving in terms huge amount of multiplication. Okay, not only multiplication, you are also saving in terms of what else? What else? If you are getting some zero valued weight, you are skipping the computation also. You are saving in terms of some memory access and some memory storage. Okay. So is it up to this part? Is it clear? Okay. So next comes as we are talking about this ReLU activation function. This is very important, and you can see nowadays this ReLU activation it has I mean, when you discuss multiple topics, there will mention about the advantages of ReLU layer. Okay. So rectified linear unit layers or ReLU layers, what it does, these put all negative input to zero and pass on positive values unchanged. As the output, again, if you revisit the output, it is your max of 0 and your input. Now, if this input is any negative value, that is getting, what I can say, again, you can say that is getting filtered and you are just passing on the 0 values. Okay. When there are integer values, then it comes, then you have to check which one is maximum. But when there is 0 and the any negative value, of course, you can pass on the 0. And if when you are passing on that 0 value in the next layer, of course, that is again saving in terms of computation. Because when you are checking that you are getting some 0 valued weight or 0 valued input, you are directly skipping the unnecessary computation. Okay. So that is one advantage of applying ReLU layers. That is in between, if you are applying some ReLU layers, that is basically decreasing the computation, amount of computation in the next layers. Okay. Since many layers in CNN classification algorithms only output positive values when certain features are present, a large amount of, sorry, this part is amount of outputs will be 0 and do not have to be, no need to consider them for any kind of further computation. Okay. So thus the ReLU layer helps you and saves some additional energy. It helps in additional energy reduction. Okay. This way, what I mentioned, that way, when you will do your assignment, you will basically judge all this activation. Now, keeping in mind these two features, that first you will consider the shape, and then you will consider, comment whether they are saturated or non-saturated, and also how, in which way they are contributing to save the energy, whether they are saving they are contributing in terms of saving energy or not. That you will comment. Okay, that will be your assignment, because that way you can understand why we are doing this assignment. That way you will understand when for one embedded scenario you are developing one network, one CNN or any this type of network. So for CNN, you will get the idea what type of activation functions will be meaningful to be considered. Of course, the first day when we discussed about activation function, if you remember that, we discussed that is entirely dependent on the output, what we want, what type of application we are working on. But along with that, we will take care when you will deal with multiple types of activation functions. Like you have one ReLU, you have one leaky ReLU. Now you will judge in these points that whether leaky ReLU will be good for your embedded scenario, or your ReLU will be good for your embedded scenario. So here we are not only considering the application, the outcome we are expecting. We are thinking in terms of energy saving. We are, thinking in terms of operation saving, like computation saving. We are using suitable activation function, how we can skip some unnecessary computations. So is it clear?
Ma'am?
Yes.
Leaky ReLU will as per my understanding, leaky ReLU will not be not result in any energy reduction, as it will allow.
Yeah, that you have to study exactly. That you so you can you go through these shapes and you go through their properties. Then only you can comment, right?
Okay.
Okay. So that comparison exactly you have to do. That which one will be meaningful, or with the light of energy saving perspective, or with the light of computation saving perspective, are they same? Or if you choose some other activation function, you are expecting some gain. Okay, that is the objective of this assignment. Fine. Is there any question so far? Everybody? Now we will talk about the fault tolerance. Fault tolerance means this is fine. You have done the activation, quantization, or you have chosen a modified activation function where you are getting this type of advantages. You are introducing sparsity, you are reducing computation. But what about your accuracy? Accuracy or fault tolerance means here in this context that when you have to, let's say you have to work on some 5, 3, 2, 4, 6 these value, okay, but you are applying the quantization and you are working on this 5, only these value. That means you are allowing some error, okay, within your computation. You are working on some videos value or some modified value. Maybe you can consider the modification of the difference with your actual value and your considered value. The difference you can consider as that is your error. So you are working on a particularly some erroneous value. Now what about your computational accuracy? How much you are losing? That means whenever you are applying this quantization or with this quantization, you are going one step ahead and you are introducing some number of zero weights, value weights with this proper calibration on your activation function, etc. How much error actually you are introducing? So that you have to consider, because if that while doing all these things, okay, you are saving energy, you are saving timing requirement, you are skipping computations, but the accuracy that is required, that is not suitable, that is not acceptable, okay. So that's why we are considering here the how much fault tolerant your network is. So when we are considering these type of quantization, this introduction of these type of errors, you can think what will be the reduced computational accuracy that we have to consider. Okay, so we will discuss first what are the experiments they have discussed. It is given in the book, in literature, what are the experiments that was done to understand that what is the relationship between this accuracy and this introduction of these errors or quantizing or introduction this sparsity. So let's first talk about the type of experiments, then we will more discuss them in form, we will discuss them in some formal equations. So this first we will talk about this space-time fixed point neural networks, okay. Now space-time means, as we discussed before, we are introducing this type of quantization, or we are adding this type of calibration and then sparsity in the space-time, okay. So of course they are working in at low precision, that you understand. So this is we have already mentioned that the pre-trained model, at the training step, we have used some floating point numbers and quantize before the inference. So that is the concept of space-time fixed point neural network. Okay. That means post-training quantization. And these generally, whatever these experiments, these when we try to get that relation, that what is the relation between this accuracy and this introduction of faults or errors, these experiments was that was done on 3 types of data sets, okay, and 3 types of networks, okay. Now why that was this LeNet 5, that is a small network. So basically it was evaluated, it was experimented on one very small network, and then a medium sized network, and then a very large network, huge network. So you see the first one, it is we are mentioning, that is LeNet 5. Okay, this is a very small network with 2 convolution and 2 fully connected layers. Okay. Next comes this, the CIFAR that was done on CIFAR 10 dataset. So this CIFAR-Quick, that is a medium-sized architecture. Okay, where they have considered the number of layers that is increasing now. So from 2 to it is 3 convolution layer and then 2 fully connected layers. It has more filters than LeNet 5. So that is more complex, you can understand. Next comes the AlexNet. Okay. AlexNet is a large network. So here you can see the number of fully connected layer and the fully connected layers are it is same with CIFAR 10 and CIFAR Quick, but we are increasing the number of intermediate convolution layers. Okay. So on these 3 types of data sets, 3 types of architectures, these relation was evaluated, this quantization relations. And here are, okay, before that, if you do not know, here is a term used. This is the top 5 accuracy. Okay. So if you do not know, some of you, so just do, this is one simple example I have taken. You can search it Google also. So what we mean by this top 5 accuracy of top 5 error or top 1 error or top 5 or top 1 accuracy, you can see in different experimental results we see these terms. Okay. So just we should understand this with a small example. Let's say you have given a multiple images. Okay, pictures of images or pictures, whatever it may be. So of few fruits. Okay. Maybe the picture you have got, that is a blueberry. Okay, according to this example. Okay. And your model, it is predicting these prediction results with some probability. Okay. You have cherry, raspberry, blueberry, etc. These are the values, probability values. Okay. So according to your outcome, according to your prediction result, the picture you have predicted, your predicted level is this. This is cherry. Okay. Because this is with this is the probability value is high, 0.55. Now when we are talking about top 1 accuracy, that means we have one single predicted level. Okay. And when we are talking about top 5 predicted levels, that means we are identify if my predicted level, if my predicted level belongs to any of these top 5 levels. It is not that I need to, here you can see when I have identified the blueberry, if I have identified that as the blueberry picture as exactly blueberry picture, if my predicted level and my true level is exactly same, when I'm considering just one single prediction level, okay, then it is, we are considering it is top 1 accurate. Okay. Whereas when I'm considering this top 5 predicted level or top 5 accuracy, top 5 error related to that, what I am doing, I'm checking this the output. I'm getting cherry, but these cherry, you can see here, these cherry belongs to this top 5 predicted levels. This blueberry and this cherry, this belong to that same top 5 predicted level. So here this is, there is a match. We are considering that this is a match. So when we are considering that top 5 accuracy, this is a bit different with the top 1 accuracy, because we are considering not exact predicted level, but we are considering a set of levels, and according to that we are considering if my predicted level belongs to that set or not. Okay. That is, that way it is written that it reaches a top 5 accuracy. Okay, so now I think you understand that it is not exact top 1 accuracy, it is top 5 accuracy of 80%. So now come back to this, is just since this term is there, so that's why I mentioned. Now Now come to the quantization steps. Okay. Yes. So now you have identified, I mean, you have some input bits. The quantization steps mean you are defining some algorithm. You are defining based on your previous calculation. You are defining one function based, and you are taking your input ranges. Based on that, you are putting your input value. So you are defining one interval basically. There you are mapping your input value, or it may be your input weights. So we will discuss this clipping algorithm in detail. Maybe let's. So this is the basic idea of what we do in the quantization step. First we finish the types of quantization, then we will come back again in this clipping. So when we are talking about this types of quantization, there are two types of quantization. Okay. In this example or in the experiments, it was evaluated. First one is single quantization setting. And the next one is per layer quantization setting. Okay, that means as from the name, I think it is quite simple. You can understand single quantization setting means you are for all the layers, you are considering uniform quantization. Okay. Whereas in per layer quantization, you are considering each layer, you are considering, and you are quantizing separately. Okay. So based on that, you can see here, this is the this is for this from these symbols you can identify. One is for the output for AlexNet, one is shown for this Zephyr, and another one is shown for LayNet. Okay. And you can see the quantization bits here and the relative accuracy. Okay. So from this, this is 0, 5. So this is increasing in this direction. Okay. So according to that, you can see that after this relative accuracy, okay, after a certain bit, quantization bit size, it is not changing anymore. That means when you are considering 0 to 5 to up to this, there is a dip fall in accuracy. But after this is quite constant. Okay. So when the meaning is that it is, based on your network, based on your input data set, and based on the weights, the ranges of your weights, it may happen that when you are doing the quantization up to a certain threshold, it will not change, it will not affect your accuracy anymore. Actually, in the result they got in practical case, it was shown that typical benchmarks that if you see the experimental results, that from 32-bit floating point inputs and weights, when you are actually quantizing to 1 to 9-bit, at least 9-bit fixed point, so that is a huge reduction in terms of number of bits. You are basically having some 1% of accuracy loss. That means this huge reduction in bit. When you are talking about bit size reduction, of course, we will see how this bit size reduction can actually affect the energy reduction. But as of now, at least this much we can understand. When you are initially we are storing 32 bits. Now we are storing around 9-10 bits. So that way, it is a huge number of bit size reduction. Bit size reduction means in terms of memory reduction. And also another energy reduction that we will see next. So this is the experimental result, that whenever we are applying quantization properly, that huge gain we can incur in terms of memory income from computation side, whereas we are just losing in our accuracy a bit, 1%, 2%, very less accuracy loss. So based initially, based on these experimental results and some heuristics, it was claimed that that's why we consider these network structures, this type of CNN network structure, they are essentially fault tolerant. Okay. So it is clear, right, that what we mean by the fault tolerant. That means when we are applying this error, or whenever we are applying this fault, quantizations, we are saving in terms of computation, we are saving in terms of memory, but accuracy loss is very less. That means your network is very much tolerant to change of these small changes, this weight size changes, or there's input size changes, and that's why this is a fault tolerant nature of this type of DNN or CNN networks, and we are exploiting that to use them in our embedded scenario. Okay, you can see these are not very when people actually observe this fault tolerant nature, this is not very old results. This is 2016, right? So that way, initially these are observed how you can quantize to a fixed point, but these results are not very old, where it was shown that with proper this type of quantization, we can actually lose very little. We can there the actual accuracy losses very little. So that way, this is, you can see here the both type of scaling was applied. One is single quantization and another is per layer quantization. In both cases, the accuracy loss is not so significant. Okay. Next, what you are getting when you are applying this single quantization, you can again see this. Again, from these. Okay, 1 second. Yeah. From these graphs, again, it was observed, see this layer one, for layer by layer, when you are applying, that is per layer quantization. These are the plots for this per layer quantization. So based on the parameter values, they've actually considered this probability range distribution. And there they have observed, from these type of plot, they have observed for per layer what quantization they are applying. That means when they are mapping, see, you can see there, it is not always like we are chopping from floating to integer. We are changing the range of data inputs or weight inputs we are considered. So when we are doing this per layer quantization, you can see here in layer 1, it is working within a particular range. Whereas in layer 6, it is working on within another range. And then that way it is minimizing the required bits. Okay. So when we are doing the quantization, our first objective will be to check what will be beneficial. What, should we do this single quantization, that I apply the same chopping for all, or the per layer quantization? Of course, to decide this per layer quantization, that is costly, but that gives your some idea, some basic operating point you can set if you go layer by layer, and this will help you to consider the energy accuracy trade-off better. That means whenever you are reducing the bits, you are reducing the there is a reduction as per energy requirement, but there is also some reduction in case of accuracy. Whereas we want the energy reduction, we do not want this accuracy reduction. So that is a trade-off. And how far there is a reduction in energy, and how far is the amount, how far accuracy loss we are actually obtaining. This is the trade-off, and this we want to, this accuracy reduction we want to reduce, whereas this energy reduction we want to maximize. Okay. So this is for, okay. Now still, whatever we are doing, we will discuss how, this point we will discuss in detail, that next, that how much energy reduction we are actually gaining when we are reducing some bit. So that we will see. But before that, there are two limitations of this space-time computation or quantization. That means there is no control over the ultimately used number of bits. That means you can actually allow as much optimization possible, but of course you have to check the accuracy. And the second thing is that if you observe this graph pattern, this is same for, actually they have tested this multiple data sets, multiple types of networks, but this graph pattern is same. And it is showing, can you tell me one observation what you can get from this graph pattern? Anyone? What is your observation according to their graph pattern? See how this quantization bits are increasing and what is the relative change of accuracy.
Ma'am, hello.
Hello, yes.
Ma'am, in parallel quantization, we achieve accuracy earlier
Yes.
than the full quantization.
So it is a better. I mean, it is easy to handle that get the idea about that trade-off. Yes, this is one thing. Per layer, we are achieving it before. But I'm not telling about the comparison between uniform or per layers rescaling. Whatever you told, you're right. But I'm telling about this graph.
Ma'am, like we cannot decrease the quantization arbitrarily. Like if it is too small, then the performance will go down.
Yes, it is true. And it is dropping suddenly. See this? This is dropping very suddenly. That means you have to gradually increase the number of, gradually control the quantization so that it should not drastically. You can see here this quantization with just for this small change, there is a huge change in accuracy level. That means there is drastic increase or drastic decrease. So that's why you cannot, that you are correct, that you cannot randomly change the quantization bits. Then you cannot get the idea what will be your suitable quantization bit requirement for that particular application. You have to increase gradually and check the threshold point where that for that you can achieve the maximum accuracy, or not the maximum accuracy, at least maybe achievable or acceptable accuracy. So for that you have to increase that quantization or control the quantization gradually, not randomly. So that way it is telling that accuracy degrades quickly at a certain cutoff point. Below this computation, below that, this precision, that algorithm, that whatever model you are working on, that will fail. So that's why this is a very critical point, that just for your quantization, that error at up to a certain threshold, it is fine, and it will give you some accuracy related to very close to your maximum requirement, very close to your, as per your requirement. But after that certain cut point, it will degrade in a certain way. So that way you have to get the actual point for actual number of bits, actual amount of quantization that you can apply for your particular application. Okay, this is one thing. Now the second thing, we are repeatedly telling that, okay, we are applying, reducing bit size, we are doing quantization, we are reducing bit size, and my energy is degrading. That is good for our embedded scenario. But here we will talk a bit about how much energy gain is possible when we are going for such low precision networks. Okay, so when we are actually this is a very basic definition. We maybe for a general digital system, when we compute power, okay, so we consider this equation, that is, we are considering the total power with some leakage power. Along with that, we are considering I will tell one by one what does it mean if someone is not acquainted with this, but it's a very basic equation. We consider the dynamic power and the leakage power. And this is alpha is a circuit switching activity. Okay. So what is switching activity? What do we mean by circuit switching activity? Anyone? Especially for electrical background students or electronics.
Ma'am, like suppose there are like there can be many gates inside a circuit, so it's basically how many times each gate is like the frequency of when each gate changes output from 0 to 1.
That means signal change, right? It is a measurement of change of signal. There is the switching is there. Yes. So that is a measurement of, we tell that changes of signal values. When there is a change, that is we call there, that is a switching activity. So this is alpha. This parameter is related to that circuit switching activity. Why we are telling that? In simple way, whenever you are doing a multiplication, let's say m into b, intermediate, you are actually doing huge number. Maybe you're realizing that multiplication with some multiple b times addition. For that addition in the underlying circuits that are getting activated, that are generating signals, and that signals are changing this, that outputs, they're changing their signal values. So that way the circuit switching activity is, based on that, we are fixing this value of alpha. Okay. V is the circuit supply voltage, F is the frequency, cup frequency, C is the capacitance. Okay. So that way, the main thing is that this circuit switching, you can think, if you are considering that you are doing one addition, let's say A plus B. Okay. And this A is in bit, maybe it's, let's say it's 8 bit. Okay. 8 bit. B is also 8 bit. When they are 8 bit and 8 bit, and you are realizing them in the underlying hardware, maybe one 2 bit component, then you have such multiple 2 bits attached, multiple intermediate values are getting generated, and they are contributing to your power generation. Whereas you are reducing this 8 bit to maybe 3 bit. Of course, you can understand that can be realized with more simpler circuits, more lesser number of gates, or more signal values, intermediate signal values can handle those changes. So that way, you are applying quantization, you are reducing the bit, you are activating lesser number of underlying circuits, and you are generating less energy. And so here was one estimate, that is 12 times energy gain can be achieved by just 1% error introduction. That means if you go to the setup of this experiments, there you can see the what type of data sets, what type of operations they are doing. But this is one estimate that one, you are actually introducing some 1% of error. How you introducing that error? Of course, by this way of some quantization and some adding some forceful, that calibrated sparsity. You are doing that, and once you are doing that, you are gaining around 12 times in terms of energy. That means there is an energy reduction in your design. And when there is an energy reduction, there is a possibility that now you can take that reduced circuit with reduced energy requirement, and you can map them to some existing microcontroller or some embedded processor. Okay, so this is a bit of hardware again. Maybe some people did not like it, but since we are trying to understand how our our energy reduction will help us, we have to understand a bit about this. What we are doing, we have this chip. Okay, maybe you are running your CNN. Now that architecture, you are doing that convolution, you are doing that, then the pooling, some you have then some normalization, then some activation, you have multiple layers for that. All these operations you are doing, specifically this costly convolution, you have this weights related to this convolution filters, and then you have some inputs. Okay, and those inputs, you are actually, initially it was stored in memory. Okay, Okay, this is SRAM buffer. This is your, let's say, basic memory of your chip. Okay. Then you are taking this some local memory. We generally consider that as register. Okay. Why if we consider that as local memory? This is comparatively faster. And then we are taking here this weight, and we are taking this activation values, and we are computing here within this MAC array. Remember, now you know about the MAC array. What is MAC array? What do you mean by MAC array? What is the full form of MAC? Here.
Multiply and accumulate.
Multiply, accumulate.
Correct. Multiply, accurate. And MAC array means? Remember
It's like
last year or
basically
last?
a sequence
Correct.
of MAC hardware units which does the
Yes.
whole multiplication and convolution and everything.
We talked about one type of, we mentioned that as systolic architecture. Remember? We talked about something like that. This is one MAC, this is MAC 1, maybe M1, M2. So they are arranged, M3, M2. So this way they have some connectivity. So there is some arrangement of MACs where you are taking this weights and this activation inputs and you are computing. So this is your structure of what is going on inside your actual hardware, and this is your network that you have designed and you have to implement here. But where is the basic problem? The huge number of filters you have considered, huge data set you are considering, this 3-layer, 5-layer, huge amount of data. You can go do one thing. You can, I have already given the references. You can go to the book. You can check these papers, okay? Or at least in the book also, you can check that what is the size of this MNIST data set or CIFAR data set, ImageNet data set. Then you will get the idea how much huge amount of data you are actually handling. And when you are coming to this, any microcontroller or any this type of chip, even in FPGA also, this memory, this SRAM buffer, the RAM, what we are considering, that is very limited. So what do you have to do? You have to consider extra additional storage. This is your RAM storage. Okay, this is the on-chip buffer, and it is external DRAM storage where you are storing your data, extra activation, these weights, input values. Let's say some part you are dividing. Let's say you are considering MNIST data set. You are dividing the MNIST data set. You are chopping a few rows. You are storing it here. Some weight values and activations, and some weight values or activations you are storing here. That means when you are maybe these are the number of rows 1 to n. You have some weight values, you have some input values, and you do not have the enough memory to store all these n rows. You are just storing these m rows here. These m rows you are storing in this SRAM, and this n minus m rows you are storing in this DRAM. That means when you need them, you have to fetch them, and you are fetching them from one extra DRAM storage. Mean you are basically contributing to some extra clock cycles or some extra timing requirement. In a simple way, you can think that's why whenever you are considering the total inference time, see here written total E inference. That means total inference time. This is not only your whatever you are doing in the hardware. This is not only your computation time. You also need to consider the DRAM fetch time. That means the amount of data you have stored in your DRAM, and that as and when required, you are fetching to your SRAM, then you are fetching to your local memory, then you are computing. So all this fetch time you have to consider. Okay. So that's why we have talked so many things. We have talked how to consider sparsity. We have talked quantization, because if we now reduce the size of these weights, if we now reduce the amount of these inputs, then as much of their data possible we can put in this SRAM buffer, so we can save this DRAM part. This we don't want. So we want to save in this DRAM part, because, and then if you are reducing the total here, maybe if it is, let's say you have some weights of WI bit, and you have maybe some capital W weight values, plus you have II bits, okay, I bit inputs, and you have total I bit values, then this much of total bits you have to store. But maybe the bit size of your memory or the byte size of your memory much lesser than that. That means you are applying that quantization and you are storing them as much as possible in this SRAM buffer, so that you can save here. In this DRAM access, you can save here, because that is some off-chip DRAM. It is not inside your chip. You are using some off-chip communication, some extra, like when you see that, I think you understand, when you used to see movies from your CDs or floppies, that used to be slower. So the same concept, when you are using these type of external DRAM storage, of course you can store, you can make your inference, possible, feasible, but you are losing in terms of energy and also losing in terms of page time. So here they have shown this equation in terms of energy, because whenever you are doing this fetch operation, for that also you are actually underlying activating some gates. You are for all operations that is incurring some energy, adding some energy altogether. So at a particular time, you are basically your inference algorithm is basically contributing to the computation as well as to the DRAM fetch energy requirement. So together, this is your inference energy, and you have to check whether this inference energy is suitable to realize in your microcontroller or any embedded domain, any specific domain you are working on, because there your energy support, your power support is very low. So whether this together thing you can handle or not. Okay, so this is the thing. Now we will go step by step a bit. We will see quickly. So when we are talking about global energy, we understood that this is this DRAM plus hardware. That is our actual computation. What we have in our actual computation. Okay, before that, when we are talking about this DRAM, this is this ED is this can be represented by this. This can be modeled with this equation. First, let's understand the parameters. What we have, what parts are contributing to this energy consumption when we are fetching something from this DRAM storage. First one is that is the energy consumed to access that. That means you are going to that memory location. You are searching something. You have some address. So first thing is that you are doing that. This is your address locations in your memory, maybe M1, M2, that way. First you are doing one search. You are searching the location you need, and from that location you are fetching some data. That means you are making, in a simple way, you are searching means you are comparing whatever address you have. You are comparing that with these address location, these address location, and so on. And when that comparison is done, when there is a match, you are getting a match. After that, you are copying that value to some location of your SRAM. That means that time you are accessing some location, some gates, some storage, maybe some register or some blocks of, sorry, not register, some blocks of this SRAM. There you are storing the data. So for one DRAM access, for one DRAM fetch, so many things are going on. You have to do first run one search algorithm where you will search the exact address, then maybe one copy operation. At least in a simple way, when you are doing this memory fetch, all these things you have to do. Okay. So for that, what I mean, what parts are contributing? That is contributing when you are considering one CNN. It is based on, that is your image dimension, that is SIN. It is number of input channels in your architecture. Okay. And this is M by Q, this factor. Okay. This is called first layer factor, or this is the quantization factor you have considered. Quantization factor means this is if it is one some M, you are considering your input bits as of M size, that means M bit inputs, and you are quantizing them to some Q bits. So you have quantized them to some Q bits. So that way, this quantization factor is actually contributing. Basically, it is improving. See, it is improving your energy requirement. You are gaining in terms of the more that Q, you can understand this, you can understand that this energy requirement will reduce. Along with that, you have this refetch, F refetch and W refetch. What are they? They are the number of words that have to be refetched, stored from DRAM. That means there are two things. One is that when you are accessing any channel input values, and along with that you are considering the associated energy, you are gaining with this quantization. Along with that, whenever you are quantizing and reducing the number of total words, that means the total number of input sizes or weight sizes, you are reducing the number of words. That means you are reducing these things, refetch or F refetch or W refetch requirements, whether it is stored or fetched, anything. So that means whenever this is the advantage of quantization, that when you are quantizing, you are basically gaining in terms of storing, in terms of access time, in terms of store memory, as well as in terms of refetching and prefetching requirement. So these are the, I think you understood the values of the meaning of individual parameters, I mean individual variables in this equation. And that way, whenever you are increasing this Q value, that means you are, based on your value of this Q, you are basically reducing the value of this energy. Okay. So that way, in turn, if I go back, you are reducing the value here, this DRAM access time, DRAM access energy requirement, and you are reducing overall energy requirement. Okay, this we have seen up to this, this DRAM access reduction, how my quantization bits or amount of quantization I'm considering, how that contribute. Next day we talk more about this, how my computation energy related to my computation that can get improved. Okay. So any questions so far? Any question? No? Okay. Then you may leave now. We will talk more about the computation related energy and how quantization is helping us in that case. Okay. Thank you.
You, ma'am.
Ma'am,
Yes.
ma'am, the assignment which was given last week, ma'am, by when do we have to submit that?
No, that is this assignment. That time I have not that time get the time to explain. I thought I will finish the class, so I will extend this assignment. You are telling that I have uploaded in Teams.
I haven't seen that, but last week there was a discussion about a wake word detection.
Oh, that one with that TinyML, right? Okay.
Yes.
That one. Yes. That one maybe next week. You have to. Next week is your exam, right?
Yes, ma'am.
Next week is 5th. Next to next week, you have to show the first output. Okay.
All right.
Okay. We will set the time, the deadline there. Next to next week means that is 12th maybe. 12th is a holiday.
Yes, ma'am. 12th to
Before
17th.
Puja. Maybe we will set the date in that way. You have to submit within that. Okay.
Yeah.
Within
Alright.
that, after next week, we have to submit that. We will set the exact date in Teams.
Okay.
Okay, thank you.